So good morning and welcome back. And in the last class, we have started the discussion regarding the analog indicating instruments, and we have seen the classifications, that is, indicating instruments, then recording instruments, and integrating instruments. And we started with the uh, different parts of an electromechanical indicating instrument, and as an introductory note, we have seen the principle behind, or principle behind the, we have listed the three types of forces, that is the deflecting force or torque, or controlling force or torque, and last the damping force or torque. Okay, so on an introductory note, I have just explained what are the different effects which control the deflecting force or torque, and we will see in detail when we take the different instruments. Okay, we have to see so many instruments, ammeters, voltmeters, then watt meters, energy meters. When we discuss all those meters, we will see the principle behind the deflecting force then and there itself. Okay, and then I have briefly explained what is the controlling torque, what is controlling torque, and what is the purpose of controlling torque. And then I have explained what is the what is the requirement of damping force or torque, because there is oscillations. When it reaches the steady state point, it will never stop suddenly at the steady state point, but it swings between a minimum and maximum point. We have to avoid that, and for that we require the damping force. And then we started discussion of the supports, and we already discussed two types of supports. I hope you remember, that is the suspension type, where at the moving system is suspended between the pair of magnets by a ribbon of phosphor bronze, and then at the lower part there's a spring attached. But there was a problem. What was the problem? Vertical alignment of the moving system is required, or perfect landing or leveling of the instrument is required, and more or less this is used in laboratory applications only, because in when we go to the field, this is not at all possible. Okay, where robust or rough handling is the mode of operandi, and so clamping arrangement should be employed for supporting the moving system. So, and then we have seen a slightly improved one, that is a taut suspension, where we have, instead of top portion ribbon, we have a spring also. So top as well as bottom portion was spring, and there perfect accurate leveling is not required, but still leveling is required, and that is also used for laboratory purpose, and this can handle or withstand more shock. Okay, and then the most robust type and little bit costly also, that is the pivot and jewel bearing type support, and we have discussed that. There we have a strong pivot where we are attaching the moving system, and then at the end we have the conical type system, which is actually in contact with a jewel bearing. And I have explained that this portion is a semi-spherical circle, and this is a tip, and this tip should be as small as possible, so that this friction is very small. If the contact is very small, the friction also becomes small. If friction is small, then the power consumption by the meter itself is very small. But how small it can be? See, this one point should be kept in mind, that is, the tip should be able to withstand the stress provided by the moving system. If that is not able to withstand the stress, this portion is not be able to withstand the stress given by the moving system, then this point will break, and that the support system will collapse. So the size of the hemisphere should be decided on the withstand capability of the stress. Okay, now that is what we'll see in detail later on, all those things. And then we have one more improved version, that is this is actually supported by a spring arrangement. This will help to absorb more shock. Okay, that is more vibration, shock, when you handle a meter from one place to another place. When you keep something, when you roughly handle, there can be shocks. So that shock should be absorbed before going to the moving system. So this spring helps in that way. And then another thing is that, see, we have a moving system. Moving system carries a pointer. Pointer will be swinging in some angle. So the thing is that the center of gravity will change. we always know for a stable system, in order for the system to be stable, the center of gravity should be along the vertical line. That is along the vertical line, or the spindle. It should be around. It should be along the pivot, or it should be along the spindle. But when it deflects, the center of gravity will change. So to avoid that, so to ensure that the center of gravity is always along the spindle, that is, we have proper balance weight. So by adjusting the balance weight, we can actually maintain the center of gravity along the spindle irrespective of the position of the pointer. So if there is a deflection by theta, correspondingly you can make the adjustment here so that the center of gravity of the moving system is all along the spindle. Otherwise there can be imbalance and that they can collapse. Okay. And another thing is that this is a very important parameter, that is the torque to weight ratio. See, the torque should be very high. We discussed about three types of torque, that is deflecting, controlling, as well as damping. So these three torques should be as high as possible. Okay, so that proper deflection should be there, and it overcomes the frictional torque also. Frictional torque is always opposing these torques, so frictional torque should be overcome. If this torque is very high, then especially the deflecting torque is very high, it will overcome the frictional torque. And if frictional torque is comfortably overcome, then the consumption of the meter itself will be very, very small. That is, the performance of the indicating instrument will be very good. So frictional torque will considerably influence the performance of an indicating instrument. So this deflecting torque is very important, and that should be very high so that it comfortably overcomes the frictional torque. Okay. And one more thing is that the weight of the entire moving system should be as small as possible. Okay. If weight is large, then again the frictional torque will improve. So weight should be small as possible, or it should be light. That is why the torque to weight ratio should be as high as possible for any indicating instrument. Okay. Then we will move on to the next portion, that is the controlling torque. So two types of controlling torque is there, that is gravity control as well as spring control. So first we'll see the gravity control. Suppose now we have a moving system here. Okay, that is a controlling. We have seen some control weights there. Okay, before we have seen the controlling weights there. See, at this point we have seen the controlling weights. Okay, this is the controlling weight. So when the pointer deflects, the controlling weight also deflects. So that is what is shown here. So when, suppose if the pointer deflects by theta, then the control weight also deflects by theta degree. So this is theta. So if I extend this line, then what happens? This angle will be theta. This angle will be theta. This will be 90 minus theta. So if I resolve this, weight will be always inclined down, vertically down. Weight of the moving system at any angle will be inclined in this way. So if I resolve these two, as we have learned in engineering mechanics, this can be having two components, that is W sine theta along this direction and W cos theta along this direction. Okay, I am interested in taking this one because since I am discussing about the torque is nothing but force in the vertical distance. So this is my force, and what is my vertical distance? This is my vertical distance. So this is my vertical distance, and this is my force, which is vertical to this distance L. So this W sine theta and L will provide the torque, which is the controlling torque. When the controlling force is deflected to this point, what happens? It always has a tendency to come back. So this is the comeback tendency, or the force to come back. So this is a force to come back, that is W sine theta. So as this weight is moving to this spot, the weight also, the component W sine theta also increases. That is, if the deflection is more, this W sine theta is also increasing. That is what I made the first point. That is, when the deflecting force increases, along with it in the opposite direction, the controlling force also increases. If the deflection force is more, then W sine theta is also more. Okay. So what is that torque? That torque is W sine theta into L. That is WL sine theta. Okay. So this W and L is constant. Weight is a constant. L is a constant here. So kg sine theta. Or I can tell that the controlling torque is directly proportional to the deflection, sine theta of the deflection. This is one way of doing it. Another one is a spring control. Spring, as you all know, it has a tension. Inherently, it has a tension. we use a flat spiral spring. Okay, and this end is here. This end is attached to the meter pivot. This is the pivot, or this is a spindle. This is a top view. So one end of the spring is attached, permanently fixed to the spindle, and the other end is loosely held, which can be attached to the circuit. Okay, so this is the thickness as well as this is the width. So B and T will give the cross-sectional area of the spring. So spring has a tension. So if it moves at any angle, if it unwinds, then it has a restoring torque. If it winds, then again it has a torque in the opposite direction. So wherever the tension will be opposite to the movement, so that tension which is opposite to the movement will help to control the movement, or will provide the controlling torque. So spring control is generally used in indicating instruments. Okay, that is, if it moves, if it unwinds, then there's a torque in the opposite direction. If it winds, then again there's a torque in the opposite direction. So that will provide a perfect controlling torque. Okay, now we'll see the small equation for that. That is, this is the equation. That is, the controlling torque provided by the flat spring is, this is Young's modulus E. I hope you understand what is Young's modulus. That is, a longitudinal stress by longitudinal strain will define the Young's modulus. Then B, as I indicate, that's the width of the spring. T, the thickness of the spring. And 12 is a constant. L is the length of the spring. Okay, overall the length of the spring. And theta is the angular deflection. Okay, so how much the pointer deflects, that is the theta. Okay, so this itself, this is a constant. L is a constant, or the whole thing is a constant. So I can tell that Tc is directly proportional to theta, or this whole thing I can take it as a spring constant Kc. So Tc is Kc multiplied by theta, where Kc is the spring constant. So the controlling torque is directly proportional to deflection of the pointer. If the pointer is reflecting, if the deflection is more, then the controlling torque also will be more. This is how the controlling torque is provided. Okay, that is Tc is equal to K theta. Okay, now another thing is that we have to learn about the damping system. So what is the damping system? Damping system, I told that it is used to nullify, or it is used to die out the vibrations in and around the steady state point. This graph you may not understand, but there are three types of system. That is, over damped system, there is no oscillations. Critically damped system, still there is no oscillations. Beyond that, there will be oscillations. So that oscillations will be large in the initial period. Thereafter, that will be dying, that will be coming down in amplitude, and finally that will be resting to the steady state point. Finally that will come to the steady state point owing to the air friction and all those things. Natural damping will be there, but initially these oscillations will consume more time, and that is highly undesirable. Okay, so there are three types of damping. That is, one is air friction damping, the other is fluid friction damping, and fourth one is the electromagnetic damping. Now, first we'll see the air friction damping. So air friction damping is that here we have a chamber, air chamber, where we have a piston. So this piston is attached to the pointer. So when the pointer moves in this direction, suppose the pointer moves in this direction, the piston will come out. So when the piston comes out, the air here, the vacuum will be created here, and what happens? There is a pressure outside the chamber which is more than the vacuum. So what happens? Inherently, the piston will be forced to move inside. When the piston comes out, there is a vacuum created, which will create a pressure difference between outside as well as the inner of the chamber, which will naturally force the piston to move inside. So that force will actually die out the oscillations. Suppose if the point is moving towards this direction, then what happens? The piston will be moving towards inside of the air chamber. So what happens? When the piston moves inside the chamber, there is naturally compression of air. So when there is a compression of air, what happens? The compressed air will exert a force in the opposite direction. That is, the piston will be forced to move outside. So again, if there is any vibration in and around the point, in and around the steady state pointer, the vibrations will be nullified by the air inside the chamber. Okay, so this is the overview. This is another thing, that the scale itself is actually an air chamber. So that air chamber will control the damping. Thank you.